Okay, hi everybody. This lecture is going to cover Chapter 1 in your textbook for ETRO143. And I apologize this week that your lecture is pre-recorded, but as you know, I'm in Japan this week, but I will be back next week. And Nick, I'm sure, will do a very good job substituting for me. But anyway, here's your lecture, which has been pre-recorded. So moving on. This is our textbook, Digital Electronics, A Practical Approach with VHDL by William Kleitz. So VHDL is a hardware description language. That's what it stands for. But basically, you're able to take the function on integrated circuits and describe it with a software language instead. In this course, we will be doing both. We will be doing designs that look structural with gates. These are gates in this picture down in the boxed in orange. These are AND gates and OR gates and NOT gates they're called, which you'll learn about. Or we could describe it behaviorally with language, Boolean algebra in particular. So a lot of this course might seem a little bit like a math course, but it's all Boolean and logic math. And in the end, we can make our own integrated circuit if we want. So we will be doing digital electronics both the gate design approach and also the VHDL approach, because that's what modern digital electronics involves. So anyway, in Chapter 1, we are going to learn about number systems and codes. So we will be learning 4 different number systems and 2 codes. Our number systems are decimal, binary, octal, and hexadecimal numbering systems, and you'll be able to convert between any one of these numbering systems. And we will learn 2 codes. One code is called BCD for binary coded decimal, and the other code is called ASCII. And those of you who have taken a programming class with me already know what ASCII code is. And those of you who did not, you will get exposed to ASCII this semester. So this is a digital course versus an analog course. In ETRO 120 and 122, we are learning analog circuits that whose voltage or current is a continuous signal. Also, much like temperature or pressure or audio signals or velocity, these are signals that are all continuously changing. This is opposed to a digital signal. A digital signal is represented by on-off states. So you can only have either on or off, and that makes the signal be digital. So on might be 5 volts and off might be 0 volts, but we represent that on paper, and we do a lot of our design on paper by saying 0 volts is called a 0, and 1 volt is represented with a 1. So we have this numeric representation, zeros and ones, that make it a digital signal. So here's another illustration out of your textbook, actually, of analog versus digital. So in this signal, this is a voltage signal that's continuously varying. It's a smooth line, right? So that makes it an analog signal. But this signal, which is off, on, off, off, on, off, on, off, is an analog signal. As a matter of fact, a digital signal. As a matter of fact, we could even represent that by saying this is 0, 1, 0, 0, 1, 0, 1, 1, 0. So now I've converted that into a digital signal, and I've given it a numeric representation here in binary. We can have an analog watch. The hands are turning continuously, and we can have a digital watch where things are displayed either. If you look at this digital watch, like for example the number 8, if you look at the number 8, how it's displayed, it is literally made up of these 7 segments. 1, 2, 3, 4, 5, 6, 7. Yeah, it's the 7 segments that make up this number 8. But any of the numbers can be represented by which one of these 7 segments you turn on or off. So once again, we have an on-off situation to display the numbers on this digital watch. So here's another example. I'm taking this analog waveform and I'm going to digitize it. So that means I have to convert something that's an analog voltage this is probably 1 volt here, 2 volts here. They have it coded specifically. So this is at 2 volts, 3 volts, and this is at 4 volts. 4 volts, and they've represented the numbers 2, 3, and 4 in a binary numbering scheme. So an analog signal that's at 2 volts gets converted to digital using a device called an analog to digital converter. So in this case, the analog number 2 gets converted right here to the binary number 2 with an 8-bit representation. So here's my digital output that's equivalent to 2 volts. So if those of you who already know binary, and I actually think that's most of you, that's, as you can recognize, that's 2, that's the number 3, and that's the number 4. So anyway, so that was the analog to digital conversion that just occurred. Another illustration out of the textbook is that you can go from analog to digital, and then you can go back digital to analog. So here this lady is singing, making an analog sound. It gets recorded with an analog to digital conversion takes place, and that's how it's stored on a CD in digital format. Old record players, old vinyl record players, stored the information in an analog format. But here we are in digital format. Maybe it's 8 bits resolution, which means it had 8 different voltage levels it could be recorded to, but usually they're 12 or 16-bit. And then a CD player is actually a digital to analog conversion, so it will convert it back to a continuous analog signal, and then you can play it to the speaker. Your textbook has this example. I'll go ahead and do it for a moment, even though it's a little bit, I don't know, could be a better example. So it says digital representations of alternative energy sources. So you can do digital representations of energy, different energy sources, but anything really that has an analog varying voltage or current level, you can convert to digital. And a lot of things have sensors, like sensors for wind, temperature, and these are all analog quantities, and they must be digitized before the computer can use them and understand them and give you any kind of results. So pretty much we live in an analog world, but we interface it through all of our digital instruments, computers, etc. So one of the other advantages of a digital waveform is what I used to call in the industry its noise suppression properties. So if I have an analog signal here and there's some kind of a noise, the noise is the squiggly lines shown on here. So there can be noise riding on my analog signal. In an audio signal, that could be static, for example, on top of the audio signal. But if you've converted this signal to a digital signal, the noise might be there somewhere in the signal, but this still looks like a 0 and this still looks like a 1. So it cleans up this squiggly mess of noise. This is actually called high frequency noise, but it cleans up this squiggly mess of noise and you don't ever see it, because here I get a bunch of voltages, but over here I still get one, looks like 1, 0, 0, 1, 0, 1, 1, and you don't see or hear this noise that is here. So that's one of the, called the noise suppression that can occur with digitizing a signal. So one more example out of your textbook, just to cover the examples. This is an example where you're getting lots of different analog signals from, they said it's a solar energy system, but whatever, all kinds of analog signals. They go to a device called a data logger, which I have shown down below. The data logger takes the analog signal and converts it to digital, and then the computer can use it. So inside this data logger, what it does is it goes and it samples the first analog input signal, the second one, the third one, and it samples them one at a time. It goes through and it gets this voltage, 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 and then each time it converts each analog signal to a digital value, and it goes into the computer. This process of sampling first this one, this one, this one, this one, this one, it's called multiplexing because you're just sampling each voltage and then one at a time. So it's time multiplexing. Okay, so that was kind of the introduction of analog versus digital. Now let's actually go into the meat of the chapter, which is about the number systems. So the rest of this chapter is going to seem a lot like a math course, but rest assured we need this to do all our binary and digital and hexadecimal designs and going forward. So we're going to study 4 different number systems. The base 10, which is our number system that we always use, 1 through 10, counting to 10. Base 10 is called a decimal number system. Base 2 is binary number system. Base 8 is called the octal numbering system, octal for 8. And base 16 is a hexadecimal numbering system. And you can actually come up with any base numbering system you want, base 3, base 4, base 5, doesn't matter. You can make up any kind of base systems that you want. There's even a numbering system to the base E, where E is the number 2.73, etc., 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 that we use in describing our RC circuits that decay or charge up. Remember that from ETRO120 last semester? The number E? Those are called natural logarithm systems when we work there. So you can make base to any number. It doesn't have to be an integer. You can make a numbering system in any base that you want. But we're going to pick base 10 because that's what we learned since we were in kindergarten. Base 2, 8, and 16 because these are convenient systems to work in when we're dealing with digital electronics. But we must be able to convert between these different number systems. So that's what a lot of this rest of this chapter is about. So we'll do some background first. It may seem trivial, but it has a point. So we'll look at the decimal numbering system first, and that's the base 10 numbering system. So base 10 means that there are 10 possible digits, and each one has to have a unique symbol. So you have 0 through 9. That gives us 10 unique digits. After that, we have to start repeating, right? 1, 0, 1, 1, 1, 2, 1, 3, 4, 11, 12, 13. So base 10 means 10 unique digits. A couple of other terminology things. This is the least significant digit. In binary, we'll call it the least significant bit for LSB when we're in binary. And this one is the most significant digit. If we were in binary, it would be the most significant bit. But right now we are still in decimal. So that's least significant. This one is most significant. And then we have this thing called a weighting factor. So the weighting factor is how you determine what this number really means. So let me give you an example. So I have the number 872 base 10, and when I do a little subscript like that, that tells me what base numbering system I'm in. So 872 in base 10, and I said that the weighting factor was a 10. So how you figure out what this number is using weighting factors, this is the 10 to the 0th place. This is the 10 to the first, 10 raised to the power of 1 place. And this right here is 10 raised to the power of 2 place. So the most significant digit has a weighting factor of 100. And this one, the middle digit has a weighting factor of 10. And the least significant digit has a weighting factor of 0. And how we break down this number, which you've probably done since about 1st or 2nd grade, is that we have 2 times 10 to the 0, which equals 2. And then we have 7 times the next weighting factor, 10 to the 1, which is 7 times 10, which is 70. And then we have 8 times 10 squared, 8 times 100, which equals 800. And so this is how the number breaks down. Add these up, 2, 7, and 8. So we're very familiar with this, and we will apply this same weighting factors technique to figure out what our binary or our octal or our hexadecimal numbers really add up to in decimal, because we're most used to dealing with things in decimal. So that's the weighting factor. Weighting factor is 10 for binary, for decimal. So now let's look at binary. Most of you, I think, are in Cisco, so binary will be very familiar to you, but we will go over it anyway, and the techniques that we're using in the binary system to convert between binary and decimal, because some of these techniques will also be used in our octal and hexadecimal system. So binary is a base 2 numbering system, which means that we have to have two unique characters to represent any number. Our two unique characters are a 0 and a 1. Our weighting factor, base 2, our weighting factor is a 2. So when we convert our base 2 number to base 10, we are going to use powers of 2. I'm actually going to cover two different conversion techniques for converting binary to decimal. One is called the weighting factor technique, which is sort of what I just illustrated in base 10. So a digit times the weighting factor. But there's another technique that I'm going to show you that I don't think you guys know already, which is called successive division. And this is useful so that we can also deal with fractions. So here's our binary number, an example binary number down below. And once again, I'm going to refresh your memory that this digit right here is the least significant bit, and the one over here is the most significant bit. Important terminology. Other terminology that we need in digital systems. A bit is a binary digit, so it's a 0 or a 1. That's what a bit is. A nibble is 4 bits, so 4 bits together makes a nibble. A byte, B-Y-T-E, is 8 bits, and I gave an example right here. There's 8 bits. 8 bits makes a byte. A word generally is 16 bits. A D word is a double word, is 32 bits, and a Q word, quad word, is 64 bits. D word and Q word are a little more obscure, and so is nibble for that matter, but nevertheless they are genuine terms in the digital world. So in binary numbering system, we use powers of 2 as weighting factors. So our least significant bit will be multiplied times 2 to the 0. Well, 2 to the 0 power is 1. 2 to the first power is 2. 2 squared is 4. 2 cubed is 3. And just to refresh your memory, sometimes it's useful. For example, what does 2 to the 5th really mean? It really means 2 times 2 times 2 times 2 times 2. That's 5 times. That's what 2 to the 5th means. And if you do that math, you'll find out that that's 32. 2 to the 6th is 64. 2 to the 7th power is 128. So these are going to be our weighting factors for any binary number that we want to convert to decimal. Well, we're going to do it first with the weighting factors technique, and then we're going to do it by the division technique. So let's do an example with weighting factors. I want to convert this number in base 2 to decimal, which is base 10. So, and we want to use the weighting factors technique. 0, 1, 0, 1, 1, 0. So this is the 2 to the 0th place, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7th, which is 1, 2, 4, 8, 16, 32, 64, and 128. Let's make this so you can see it. Can't draw that line very well, can I? I think we're okay. Maybe I'll put commas in here so we don't blur it all together too much. So how do I find out this number in decimal? I have 0 times 1, which equals 0. And then come down this column. I have 1 times 2 to the 1, which equals a 2. Come down the next column. I have a 1 times 2 squared, which is a 4. Come down this next column. I have a 0 times 2 to the 3rd, which is still a 0. Come down this next column right here. 1 times 2 to the 4th, which is a 16. 0 times 2 to the 5th is a 0. 1 times 2 to the 6th, write that a little bit better, is 64, and 0 times 2 to the 7th is a 0. And now what I do is I add all of these numbers up right here, and it will come out they add up to 86 in base 10. So this is called the weighting factors technique for converting my base 2 number binary to a base 10 number, which is decimal. So this number in base 2 equals 86 in base 10, or decimal numbering system. So that's the weighting factors technique. I think this is what you did completely in Cisco. The other way you can convert a binary number to decimal is by successive division by 2, and I think that that's best done by an example. So I will proceed to an example. Actually, yes, I will proceed by an example. Actually, this is not quite the division method, but I'll show that to you in the next slide. I have my slides slightly out of order, but I'm going to show you now how to convert a fractional number. You can see this is something point something in binary to decimal. And so let's determine our weighting factors here. So I'm going to draw a little bigger this time. Pen 1 0 1 1 point 1 0 1 0. So the weighting factors are 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. But what are the weighting factors over here on the other side? These are 2 to the minus 1, 2 to the minus 2, 2 to the minus 3, and 2 to the minus 4. So these weighting factors are still valid. So I have 1 times this is a 1, plus 1 times this. This one is a 0. 0 times that. And this one is an 8, right? And I'm going to continue to add. I'm not going to do a decimal point. I could do that. But what is 2 to the minus 1? 2 to the minus 1 is 1. Well, this whole thing, 1 times 2 to the minus 1 is 1 times 1 over 2. What's 2 to the minus 2? Well, this one's a 0 times 1 over 2 squared. And this is a 1 times 2 to the minus 3. 1 times, what's 2 to the minus 3? It's 1 over 2 cubed. And this one is a 0, so I won't do the 0 one because I'm running out of room. So this is 8, 9, 10, 11. This part comes out to be 11. And I'm going to add this part. This part right here is plus 1/2 plus 0 plus 1/8. 1 divide, that's 1/8 right here, right? So it's 11 plus 0.5, that's 1/2, right? Plus 0.125, because that's 1/8. And so I get my final answer is, doing it in my head, 11.625 in the base 10 numbering system. So the weighting factor still works, even if it's a fraction, which this is definitely a fraction, because there's a decimal point there, not to be confused with being in the decimal numbering system. But I do have a decimal point indicating that this number has a fractional portion to it. So that's how we convert using the weighting system with a fractional number. So now that was 2 examples of going binary to decimal. Let's go decimal to binary using 2 different methods. So okay, let's do the first method, which has to do with the weighting factors actually, which I think you're probably most familiar with already. So remember that I like to just write it down. 2 to the 7th is 128, 2 to the 6th is 64, 2 to the 5th is 32, 2 to the 4th is 16, 2 cubed is 8, 2 squared is 4, 2 to the 1 is 2, and 2 to the 0 is 1. So you take your number, 133, and you figure out what is the biggest number you can subtract from it. And like I could subtract 8 from it, but I could subtract 8 from it many times. And so I don't want to do that because I can only have something occur once. I'll show you what I mean. So 128 is the biggest number I can subtract from it. And 2 to the 8th, I can't do 2 to the 8th because that's 256 and that's too big, right? But I can subtract 2 to the 7th from it. So I can subtract 128. And when I do that, I have 5 left over. So I go over here and I say this is my 0, 1 spot, 2 spot, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4 position, 2 to the 5 position, 2 to the 6 position, 2 to the 7th position. And I'm just going to kind of do a little chart here. So 2 to the 7th does go into this 133, so I'm going to put a 1 there. Can I now subtract 64 from it? No, so I'm going to put 0 here. Can I subtract a 32? No, so I'll put another 0 here. Can I subtract 16? No, so I'm going to put another 0 here. Can I subtract 4? Yes, I can. So I can subtract 4, so 2 squared should get a 1 right there, right? And then I have this left over. Can I subtract 2 from it? No, so I'll put a 0 there. Can I subtract 1 from it? Yes. So 2 to the 0 is one of the numbers that will work. And so now I've converted 133 in base 10 to 100000101 in base 2. So that's the first method of converting decimal to binary. A little bit intuitive, I think. Let me show you the next way. Let me give me an extra slide here so I can do it. I'll put the same number back on here, which was 133 in base 10, and I want to know what it is in base 2. And I'm going to use the divide by 2 method now. So this is the divide by 2 method. Now these methods I'm also going to apply to our other numbering systems. So anyway, I say, what is 133 divided by 2? And the answer is 133 divided by 2. Why can't I do that in my head? So the answer is, whoops, pen, come back, 66 with a remainder of 1. So R for remainder. So now I say, what's 66 divided by 2? And it equals 33 exactly, remainder of 0. 33 divided by 2 equals 16, remainder of 1. 16 divided by 2 equals 8, remainder 0. 8 divided by 2 equals 4, remainder 0. 4 divided by 2 equals 2, remainder 0. 2 divided by 2 goes 1 time with a remainder of 0, and 1 divided by 2 equals 0, remainder 1. So this is the most significant bit, this is the least significant bit, and if I write this number down, I get 1, 2, 3, 4, 1, 2, 3, 4, 1, 0, 1 in base 2. And if I go back one slide, sure enough, that was the answer I got by using the weighting factors method to convert decimal to binary. So this is the weighting factors method on this slide. This one's weighting factors method to convert the decimal to binary. And this is the divide by 2 method of converting my decimal to binary, my binary to decimal. And we can use these same methods in other base numbering systems, which I will show you. Oh, I went back. No wonder that didn't look right. Correct me when I'm wrong. Eraser. It's not really a divide. I went the wrong way. Sorry. Okay. That's weighting factors, and this is divide by 2 method. Yes. Correct. This is my divide by 2 method of converting decimal to binary. Yes, okay. So another interesting thing about binary is I think it's just kind of nice to be able to count in our binary numbering system, just like we count in decimal. So sometimes people see the pattern then, so I'm going to go ahead and show you the pattern, and then we're going to talk about the octal numbering system next. So if I were counting in decimal, like we've done our whole life, we say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We've used up our 10 digits, and we start repeating 1, 0, 1, 1, 1, 2, 1, 3, etc. So the same thing happens in binary. We start with 0, 1, and now we've run out of digits, so now it's 1, 0. And then adding to the least significant bit here, 1, 1. We've run out now. Sometimes it's easier to see if I just write it this way. 0, 1, 1, 0, 1, 1. Oh, I can't go any further now. I've run out of digits. So it must be 1, 0, 0. And then starting with the least significant bit again. 1, 0, 1. 1, 1, 0, 1, 1, 1. Now some of you see this pattern and some of you don't, but I'm going to introduce it anyway. And so you're starting in the least significant bit part, just like you did in decimal system, and when you've used up your allotted different unique characters, then you go up a place in significance. Same thing in binary. In octal, we can do the same thing. Octal is a base 8 numbering system, so I have 8 characters I can use. Those 8 characters are 0, 1, 2, 3, 4, 5, 6, 7. After 7, I don't have any more characters to use, and I have to restart with the next significant position. So now I have 1, 0. You cannot say this is 10, because this is an octal numbering system. This is 1, 0, which is the number 8 in decimal, and then 1, 1, and 1, 2. And to be clear, we can put a little subscript 8 there to indicate that that's an octal numbering system. So octal, or base 8 numbering system, as I said, has 8 unique characters that you can work with. After that, they start repeating. The weighting factor is 8. Remember, weighting factor in decimal is 10. Weighting factor in binary is 2. So octal, the weighting factor is 8. So everything is going to be in powers of 8. The conversion techniques that we will use are similar, but I get to show you some shortcuts on this one. And then let's look at this number, 984 in base 8. This is incorrect. Why? Hopefully you got why, but because you don't have a number 9 and you don't have a number 8 when you're doing octal, right? You have the characters 0 through 7. So you can't say that that's a base 8 number because these characters do not exist in a base 8 numbering system or an octal numbering system. So our weighting factor is an 8. So here's an example of converting between octal to decimal using weighting factors. So my weighting factors are now powers of 8. 8 to the 0, 8 to the 1, 8 to the 2 power, 8 to the 3 power, 8 to the 4 power. And so I have 3 times 8 to the 0, which is 3 times 1, which is a 3. This next digit, 6 times 8 to the first power, which is 6 times 8, which is 48. The next position is 2 times 8 to the second power. 8 to the second power is 16. No, it's 64. 8 squared is 64. So 2 times 64 is 128. 1 times 8 to the third power, 8 to the third power is 512. So add 512. And then the most significant digit here is a 7. And then they have 7 times 8 to the 4. And 8 to the 4 is, oops, not times. It's 8 raised to the 4th power equals 4096. So I have 7 times 4096 is 28,672. So that's my octal to decimal conversion using weighting factors. And our weighting factors are powers of 8. Write that down. So we can go octal to decimal. I'm going to show you how to go binary to octal and vice versa. I'm going to show you a shortcut method. So, whoops. Let's say I have the number 372 in octal, so 372 to the base 8 numbering system. So one thing that you can do, this is the shortcut, is I can convert this directly to binary. So 2 in binary is 0, 1, 0. And you always have to use three digits here. 7 in binary is 1, 1, 1. And 3 in binary is 0, 1, 1. And so I've now taken my number 372 in octal and converted it to binary, shown right here, just by writing each digit in terms of 3 bits directly, and I convert to binary. Now I can also now convert, once I've converted to binary, I can convert it to decimal. So I have, these are the 2 to the whatever powers down here, the weighting factors. So I have a 0 plus a 2 plus a 0 plus a 2 to the 2 cubed is 8. I have an 8. I have a 16. I have a 32. I do have a 64. And I have a 128. I add these numbers all up, and I will get whatever the number is in base 10. So you can go either way, vice versa. I can give you a number. I will just make one up right now. I'm going to say this is my number. In binary, and I want to convert it to octal. So the thing that you do is divide it up into groups of 3 for octal. This is a 1, this is a 7, and this is a 2. So this number in base 2 equals this number in base 8. So take the binary number, divide it up into groups of 3 bits at a time, and then convert it directly to octal. So let's do some examples. This is my example. Convert this number in base 2 to a number in base 8. I do that by dividing these up into groups of 3, starting from this direction, from the least significant direction. Don't start from the most significant or you'll get the wrong answer. Start here, chunk it up into 3 bits, chunk it up into 3 bits again, and then chunk it up into 3 bits right here. And how to make it 3, we put a 0 in front. So I can put infinity zeros in front, it doesn't change the number, right? So converting directly, I see that this is a 1, this is a 7, and this is a 2. So 2, 7, 1 in base 8 numbering system. Now it says take this number in base 8 or octal and convert it to binary. So I start here at the least significant and I write the number 6, which is 4, 5, 6. That's a 6 in binary. The number 2 in binary is that. And the number 3 in binary is that. So 3, 2, 6. I have now converted my base 8 number to binary or base 2 number. This one, 326 base 8 into decimal, there's 2 different ways that you can do it. One is I can convert it to binary, like I did in the middle step, and from the binary apply my base 2 weighting factors and come up with a decimal number. Or I can apply my base 8 weighting factors right here and come up with the decimal number. So this is 6 times 8 to the 0 power, which is 1. So that's a 6. This one right here is 2 times 8 to the first power. So that's 2 times 8, which is a 16. And this one is 3 times 8 squared, which is 3 times 64. 9, 10. Oops, 6, 12, 8. Sorry. 6, 12, 18, 19. 19. And then I add these numbers up. That's 12, 13, 14. Carry the 1. 9, 10, 11. Carry the 1. 2, 1, 4. Okay, so I could do it that way, or I could have done weighting factors that were in base 2 and converted from binary to the decimal. either way that you wanted. Okay, so one more numbering system that we need to consider, and that's the hexadecimal. Hexadecimal is a base 16 numbering system, which means we need to have 16 unique characters. And our weighting factor is also a 16, so everything is going to be in powers of 16. So if I want to have 16 unique characters, right now our numbering system has 0 to 9. Those are our 10 unique characters. So we need some more, 6 more unique characters. So we use A, B, C, D, E, and F. So here I am counting in hexadecimal. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. And now I've run out of my unique characters, and I have to move to the next significant place and start over again. So now it's not 10, it's 1, 0 in hex. And hex, you can just say hex for hexadecimal, that's very common. You can say base 16, it means the same thing. So now I start repeating 1, 0, 1, 1, 1, 2. And if I were to continue that, 1, 4, 1, 5, 1, 6. I'm just going to continue over here. 1, 7, 1, 8, 1, 9. What happens next? It's not 2, 0. It's 1, A, 1, B, 1, C, 1, D, 1, E, 1, F. Now what happens? What's next? So I've ran out on the least significant digit, so I got to change this one. So now it's 2. 0, 2, 1, 2, 2, 2, 3. I'm going to continue. 2, 4, 2, 5, 2, 6, 2, 7. It's not 27. It's 2, 7, 2, 8, 2, 9. It's not 3, 0 isn't next. It's 2, A, 2, B, 2, C, 2, D, 2, E, 2, F. Then 3, 0. 3, 1, 3, 2, 3, 3, 4, 3, 5, 3, 6, 3, 7, 3, 8, 3, 9, 3A, 3B, 3C, 3D, 3E, 3F. Then it's 4, 0, etc. What happens after you get to 4, 0, 5, 0, 6, 6, 0, 7, 0. What happens after you get to 9F? What's the next number? The next number is 10F. No, the next number is AF. A0. Sorry, A0 is the next number after 9F. After 9F, erase. After 9F, this becomes a 0. This becomes one more. It's A0. Then A1, A2, dot, 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 etc. What comes after, what's the next number after AF? B0. Then B1, B2, all the way down to BF. Next number will be a C0. C0, C1, down to CF. Finally, we'll get down to the number FF. What comes after FF? 1, 0, 0 is the next number after FF. Okay, hope you see that pattern. Continuing on with our hexadecimal numbering system. Here's some things that are useful in hex. One is all of our HTML colors. All of our web page colors are encoded in a hexadecimal format. So the color red, for example, is FF in hex. FF000. The color green. This is called a red, green, blue color scheme, or RGB color scheme for red, green, blue. So if you have all ones in the first, turns out this is going to be a byte, then you represent the color red. If you have all ones in the middle byte, it's the color green. If you have all ones in the lowest byte, it's a blue color. And just for fun, I have a link right here where you can play with the colors and see them at work. Here it is. So for example, so I'm using red, green, blue color scheme. 000FF is a blue color. Green is 00FF00. And then you can get these colors in between. So if I pick a color in between, the color I've picked in between is an FF33CC. That's the color I picked right there. And there are other color schemes. There's a red, green, blue is what I'm using, but there's also some other encoding that we could use. But anyway, this is a fun little website you can play with. What do you think black is? Black would be a fun color. Black. Do I have black? Oh, that's not quite black. There's black. Black is all zeros. And white is all F's. So black is all 0, white is all F's. So must be additive. Colors. Okay. Another use for hexadecimal, those of you in Cisco know this very well, an IP version 6 address is all written in hexadecimal. Why? Because if you wrote it in binary, it would be incredibly long. So hexadecimal is the most convenient way to write it. And we'll see that that's true a lot. For if you want to have a long binary stream, it's nice to write it in hex. So hexadecimal conversions. I'm going to show you the hard way, and then I'm going to show you the shortcut way. So here's the first way, which is the hard way, with weighting factors. Remember, our weighting factor is a 16, and so everything is going to be a power of 16. 16 to the 0, 16 to the 1, 16 squared, 16 cubed. So 7 times 16 to the 0 is 7 times 1, which is 7. F. What's F? F is a 15 in decimal. So that's 15 times 16 to the first power for this position right here. And that turns out to be 240. Next one is 2 times 16 squared. So 2 times 16 squared happens to be 512. And this is A times 16 cubed. Well, A is a number 10 in decimal. A is a 10. So 10 times 16 cubed is that number, and then you add them all up and we come up with this gargantuan 41,719 in base 10. So that was a 4-digit hex number converted to a decimal or base 10 number. Now this is kind of ugly, so let's show you a nice shortcut way. Before I show you the shortcut way, I'm going to go back here to this slide for a moment. Yes, this is, no, I'm not, no, oh, okay, notice these binary numbers. They're 4 bits. It takes 4 bits to represent our hexadecimal numbers 0 through F. And F is 1111, 0 is 0000, but it always takes 4 bits to represent one of these hexadecimal numbers. And that's going to be the key to our shortcut method here in a moment. So here's our shortcut method. Convert a binary to a hexadecimal number, and then maybe to a decimal number, and vice versa. So here's my hexadecimal number, 5F. So what I do is I represent F in binary. F is a 15, and that's 1111. 5 is 0101. So now I've represented my hexadecimal in binary, and then I can apply my powers of 2 weighting factors here, and multiply, add that all up. Excuse me, I have a cold, sorry. Multiply those, weighting, multiply those binary digits by its appropriate weighting factor, add them all up, and you'll get the decimal number 95. Now, you can go easily from binary back to hexadecimal by dividing my binary number up into groups of 4. Remember, in octal it was groups of 3. In binary it's groups of 4, and then converting it directly to the hexadecimal. So let's do some examples. Sorry about that sneeze a moment ago. Okay, so I have an example here. It says convert this binary number to a hex number or a base 16 number. So what I do is I divide it up into groups of 4. Remember, in octal it's groups of 3. And then I convert this to its appropriate hexadecimal character. So this is 8, 4, and 1. It's a number 13. Let's see, A is 10, B is 11, C is 12, D is 13, E is a 14, and F is a 15. Sorry, I have to write these down. So this is 8 plus 4 is 12, plus 1 is 13. A 13 is a D. And this number right here is a 4 plus a 2. This is a 6. Yes, this is a 6. And 6 is just a 6. So 6D in hexadecimal. Now I have a hexadecimal number and I want to convert it to binary. So I convert my 9 to binary and I have to use 4 digits. So a 9 is a 8 plus 1 is a 9. That's a 9. And in A is 10. 8 must be one more, 9, 10. So that's 10. That's A or 10, and that's 9. So 1 0 1 0 1 0 0 1. Next example. Convert a base 10 number to a base 16 number. So to me, which way would I do that? To me, the easiest way would be to convert this number, the base 10 number, to a binary number, and then a binary number to a base 16 number. The other way you could do it is take 498 and start subtracting out the different powers of 8, right? So how many times does 8 squared go in there? It's actually a hard way to do it. The easiest way is to convert it to the binary number, and then after you convert it to the binary number, you can convert it to the base 16 number. So take your pick how you want to convert this to a binary number. One is by adding up the different weighting factors, the different powers of 2 until it adds up to 498. But I actually personally like the divide by 2 method. So 498 divided by 2 equals, and I think I need my calculator for that. Not really, but I'm going to. Equals 249 with no remainder. 249 divided by 2 equals, I don't need my calculator because 250 would be 125, 124 with a remainder of 1. 124 divided by 2 equals 62, remainder 0. 62 divided by 2 equals 31, remainder 0. 31 divided by 0 equals 15, remainder 1. 15 divided by 0 equals 7, remainder 1. And 7 divided by 0 equals 3, remainder 1. 3 divided by 0 equal, 3 divided by 2. Oh, these are all divided by 2's. I mean, 3 divided by 2 is 15, remainder 1. 15 divided by 2 is 7, remainder 1. 7 divided by 2 is 3. 7 divided by 2 is 3, remainder 1. 3 divided by 2 is 1, remainder 1. 1 divided by 2 is 0, remainder 1. This is the most significant bit. This is the least significant bit. And my final answer is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Oops, this is the binary answer. 0, 0, 1, 0, 0, 0, 1, 0, and base 2, which equals, now I'll split these up into groups of 4. Groups of 4. So this is a 2. This is a 15. Well, what's a 15? A 15 is an F. And this is a 1. So my answer is 1F2 in base 16. So I took my base 10 number, converted it to binary, and then my binary number, I convert it to the hexadecimal number. Okay, 2 more subjects. These are next are codes. Actually, this is a good place to take a break, and I'll do codes in the next lecture. So let's say this is a good break spot. Okay,